Reliable generalization is vital for safe ML and AI. The ability of neural networks to generalize is a key unresolved issue. In this study, we explore whether computational theory can help predict neural network generalization boundaries practically. We show that sorting tasks based on the Chomsky hierarchy enables the prediction of architectures capable of generalizing to new inputs. Some scenarios show no significant generalization even with substantial data and training time, despite models having enough capacity to perfectly fit the training data. Our findings reveal that RNNs and transformers struggle to generalize on non-regular tasks, while LSTMs can tackle regular and counter-language tasks. Only networks enhanced with structured memory, like a stack or memory tape, can effectively generalize on context-free and context-sensitive tasks. Statistical learning theory, commonly used in machine learning, underpins empirical risk minimization and generalization error estimation through a test set. However, this theory's central assumption of independent and identically distributed training and test data is frequently violated in real-world problems like distribution shifts and continual learning. Sequence prediction test scenarios, where agents are trained with sequences of length T(n) and tested with much longer sequences T(n), pose a significant challenge as they encompass all computable problems. Inductive inference is crucial in sequence prediction, where a general rule is derived from specific instances to make predictions. The challenge lies in selecting one hypothesis from multiple data-fitted ones, requiring inductive biases. Network architecture, training mechanisms, and initial parameter distributions all contribute to inductive biases, with various approaches proposed to design these biases. Balancing strong inductive biases and model universality poses a significant challenge in contemporary literature. Despite theoretical universality, gradient-based training may hinder reaching the optimal solution due to the inability to search the entire parameter space exhaustively. Published as a conference paper at ICLR 2023, Context-Sensitive Recursively Enumerable Infinite Tape Finite State Controller Linear Tape Stack Counter Deterministic Context-Free Regular Counter Finite FFNN-RN LSTM Stack RNN Transformer Tape RNN. Formal language classes correspond with neural network architectures. Our empirical evaluation locates architectures on the hierarchy of formal language classes. Each formal language class is associated with a minimal computational model automaton to recognize or generate the language. All automata have a finite state controller at their core with increasingly restrictive memory access as we descend the hierarchy. Practically render the model non-universal. Both architectural and training limitations impact the model's ability to solve sequence prediction problems in practice. In formal language theory, the Chomsky hierarchy classifies such problems by increasing complexity. This hierarchy is associated with a hierarchy of models, automata, that can solve different problem classes. Lower-level automata have restrictive memory models and can only solve lower-level problems, while Turing machines with infinite memory and unrestricted memory access lie on top of the hierarchy and can solve all computable problems. However, the unified placement of neural architectures on the Chomsky hierarchy has not been established in practice, which is the goal of our work. We conduct an extensive empirical study to discover how neural network models used for program induction relate to idealized computational models defined by the Chomsky hierarchy in practice. We investigate whether the theoretical limitations of certain neural models hold in practice when trained with gradient-based methods. For example, previous work has theoretically argued that RNNs are Turing-complete. However, more recent theoretical analyses showed that RNNs lie much lower on the Chomsky hierarchy. To complement these theoretical analyses, we conduct a large-scale empirical evaluation on sequence prediction problems. Our main contributions include conducting an extensive generalization study of state-of-the-art neural network architectures, RNN, LSTM, transformer, and memory-augmented networks, stack RNN, tape RNN, on a battery of sequence prediction tasks spanning the entire Chomsky hierarchy that can be practically tested with finite-time computation. We also open-source a length generalization benchmark that is out of reach for state-of-the-art sequence prediction models and allows us to pinpoint the failure modes of these architectures. Additionally, we show how increasing amounts of training data do not enable generalization on tasks higher up in the hierarchy for some architectures, potentially implying hard limitations for scaling laws. We demonstrate how augmenting architectures with differentiable structured memory can enable them to solve tasks higher up the hierarchy. 2. Related work. Learning formal languages. A long line of work has empirically investigated whether common machine learning architectures, including RNNs, GRUs, SCNs, LSTMs, and transformers, are capable of learning formal languages. The main insights are, these networks can, published as a conference paper at ICLR 2023, Learn Simple Counting Languages, Hodobler et al., 1997, Stivers and Grunwald, 1996, Wiles and Ellman, 1995, Rodriguez and Wiles, 1997, and the Dyke 1 language, Skachkova et al., 2018, Suzgun et al., 29a. To learn more advanced languages, RNNs and LSTMs require exponential memory in terms of the input length, Sennhauser and Berwick, 2018, as they lack an external memory structure. They are capable of learning simple context-sensitive languages, such as A and B and CN, but in a very limited way, i.e., they generalize only to lengths close to those seen during training, Bowden and Wiles, 2000, 2002, Gers and Schmidhuber, 2001. Similarly, transformers cannot learn Dyke languages for N1 in long sequences, Ebrahimi et al., 2020. Concurrent work also studies length generalization on synthetic reasoning tasks akin to learning formal languages, but for pre-trained large language models, Anil et al., 2022, Zhang et al., 2022. Thus, while prior work has investigated a single architecture on a restricted set of tasks under different experimental conditions, we provide a unified experimental protocol that spans all the levels of the Chomsky hierarchy for a wide range of models. Neural networks and the Chomsky hierarchy. It was theoretically shown that RNNs and transformers are Turing-complete, Chen et al., 2018, Perez et al., 2019-21, Siegelman and Sontag, 1994. However, these results are impractical as they rely on an unbounded number of recurrent steps and on arbitrary numerical precision. Thus, more recent work, Ackerman and Sybenko, 2020, Bhatta-Mishra et al., 2020, Han, 2020, Howe et al., 2022, Korsky and Berwick, 2019, Merrill, 2019, 2020, Merrill and Sabarwal, 2022, Weiss et al., 2018, has refined these theoretical analyses by considering linear computation steps and logarithmic precision, showing that RNNs and GRUs can, in theory, recognize regular languages, and LSTMs are strictly more powerful since they can learn a counting mechanism, i.e., are K-counter machines. Moreover, it was theoretically shown that transformers are not well aligned with the Chomsky hierarchy since they cannot recognize certain regular languages, e.g., periodic finite-state languages, while being able to learn some counter languages, e.g., shuffle duck and n-ary Boolean expressions. A different approach proposed a computational model to capture the transformer operations and used it to show which tasks could conceivably be learned by a transformer. Histograms, sorting, duck languages, Weiss et al., 2021. However, this approach only upper bounds the capabilities of a model and does not provide any insight on whether gradient-based methods will find parameters that can solve a task in practice, which is precisely the goal of our work. In that sense, our work complements the above studies by investigating how well gradient-based learning can exploit the inductive biases of common machine learning architectures to recognize languages on different levels of the Chomsky hierarchy. Memory-augmented networks. A popular approach for augmenting neural architectures with external memory is to equip a recurrent network with read and write access to differentiable memory structures, such as deterministic stacks, Das et al., 1992a, B, Greffenstedt et al., 2015, Howe et al., 2018, Julin and Mikolov, 2015, Molly et al., 2021, Moser and Das, 1992, Stogan et al., 2020, Sun et al., 1993, Suzgun et al., 29b, Yogatama et al., 2018, Non-Deterministic Stacks, Dussel and Chang, 2020, 2022, Random Access Memory, Danny Helka et al., 2016, Kurach et al., 2016, and Memory Matrices, Graves et al., 2014, 2016, Gulcher et al., 2018, Yang and Rush, 2017. Such memory-augmented networks are capable of recognizing complex languages, including tasks like copying or reversing strings, but they can only perform one computation step per input token. Thus, to solve superlinear tasks, e.g. binary multiplication, memory-augmented networks also need to be able to perform a linear number of steps per token. Freivalds and Liepens, 2017, Kaiser and Sutskever, 2016, Price et al., 2016. In a different effort, reinforcement learning has been applied to interact with discrete memory interfaces, making deterministic memory operations amenable to gradient-based training. Zaremba and Sutskever, 2015, Zaremba et al., 2016. Finally, prior work also proposed networks with read-only memory access, Suckbatter et 2015, Weston et al., 2015, or spatiotemporal connections, Couchbrenner et al., 2016. We also consider memory-augmented networks and find that memory structures are necessary to generalize on sequence prediction problems higher up the Chomsky hierarchy. Background. We now provide the necessary background on how to link sequence prediction and formal language theory, allowing us to associate neural architectures and the Chomsky hierarchy. As we want to evaluate the capability of networks to generalize to sequences of unseen length, we need a way of generating arbitrarily long sequences that all exhibit the same structure. To that end, we will consider sequences as elements of infinite formal languages, which are generated by a grammar, published as a conference paper at ICLR 2023. Chomsky hierarchy grammar types, their corresponding minimal automata and memory structures required for language recognition or generation, their production rules, and the corresponding example languages from Section 3. The production rules symbols are defined as a terminal, A, B non-terminal, alpha, beta, gamma string of terminals and or non-terminals. Alpha, beta can be empty, but not gamma. Grammar type low to high, regular, context-free, CF, context-sensitive CS, recursively enumerable, RE. Automaton memory production rules, example regular, R, finite state automaton, FSA, automaton state AAB, context-free CF, push-down automaton, PDA, infinite stack, only top entry accessible. A alpha B context-sensitive CS, linear bounded automaton, LBA, bounded tape, all entries accessible. Alpha A beta, alpha gamma beta. C recursively enumerable, RE. Turing machine, TM, infinite tape, all entries accessible. Gamma, alpha D, formal language. A formal language L is a set of words where each word is a finite string of symbols drawn from a finite alphabet sigma. For example, with a binary alphabet sigma equals 0, 1, we can describe the following infinite languages. A equals 0, 1, quam m, n, m, 0, B equals ww as a palindrome, C equals www as a word, and D equal ww describes a terminating Turing machine. Generative grammar. Languages of infinite cardinality can be generated with a finite alphabet and a finite generative grammar. A formal grammar, Chomsky, 1956, is defined by a finite set of terminal symbols, a finite set of non-terminal symbols, a distinctive start symbol, and a finite set of production rules that map from non-terminal symbols to other symbols. The set of all words that can be formed by such a grammar is its corresponding formal language. For example, the binary palindrome language B can be generated by the set of rules P epsilon 0, 1, 0 P 1 with start and non-terminal symbol P and terminal symbols 0, 1. The Chomsky hierarchy arises from categorizing the allowed relationships between terminals and non-terminals in the grammar. Recognizing a language. An automaton recognizes a language if it accepts all strings in the language and no others. For example, A, deterministic, finite state automaton, FSA, can be defined as a 5-tuple Q sigma delta Q0 F, consisting of a finite set of states Q, the finite alphabet sigma, a transition function delta, QX sigma Q, an initial state Q0 in Q, and a set of accept states F subset of Q. More complex automata, such as the push-down automaton PDA, additionally have access to an external memory structure. The Chomsky hierarchy classifies languages based on the automaton that can recognize it. All automata in the hierarchy have a finite state controller at their core, with increasingly flexible memory structures. Language classes generated by higher grammar types subsume languages generated by those lower in the hierarchy. Transduction versus recognition. In practice, learning to recognize a formal language by training a classifier on words and non-words is hard. For this reason, we consider language transduction tasks where the inputs and outputs form two individual formal languages, and the goal is to learn a deterministic function that maps a word from one language to the other. A deterministic finite transducer, defined as a six-tuple Q sigma O delta Q0 F, differs from a finite state automaton in that its transition function delta Qx sigma IU empty sigma OU empty XQ can output a symbol from the output alphabet sigma O, or the dummy token empty, at every step. Published as a conference paper at ICLR 2023, a deterministic function Fi stro O given by I equals by O between two formal languages, which is precisely what we want to learn. Thus, strictly speaking, we do not consider a hierarchy over formal languages, but over language transduction tasks. Importantly, the machines required are identical to those in the Chomsky hierarchy, i.e. FSAs, PDAs, LBAs, and TMs, except that they can now also output values at each transition, i.e. the memory augmentations stay the same. We further discuss the transition from recognition to transduction, as well as prior approaches in Appendix A.1. Methods, problem setup. For each task, we define input and output languages LI and LO with their corresponding alphabets I and O. The goal of a task is to learn the deterministic function f that maps words XLI to words YLO, i.e. language transduction. To that end, we consider models p theta while x as conditional distributions over next possible sequence continuations with parameters thet. We one-hot encode the tokens in both languages Li and Lo as vectors length of I and wstO, respectively, denoting the corresponding jth entries of the ith one-hot tokens xi and yij. We use gradient-based training to minimize the average cross-entropy loss, where cxy minus 1yiy till x denotes the per-example loss. Note that we do not use autoregressive models, but rather append y empty dummy tokens to the input. Thus, the model will know when the input sequence x has terminated by reading the first empty token. We compute the per-sequence accuracy as the percentage of correctly predicted tokens, i.e. AXY equals 1y I1 on argmax JYIJ, argmax JPXJ. Moreover, we compute the overall performance score as the per-sequence accuracy averaged over all sequences of unseen length. We run our experiments over 10 different network parameter initialization seeds and report the maximum score instead of the average, as this better indicates if an architecture is capable of learning the right algorithm at all. Tasks. For each level of the Chomsky hierarchy, we define various sequence prediction tasks, ranging from modular arithmetic R to binary addition CS. We place the most emphasis on CS tasks as they are currently out of reach for state-of-the-art models and thus provide an ideal benchmark to guide future research on architecture design. We list the tasks and provide a full formalization. Although seemingly simple, these tasks are well-known examples in the theory of computation and concisely demonstrate the key properties of the grammars in the Chomsky hierarchy, i.e., counting, repetition, long-distance dependencies, and hierarchy. Note that the levels of our tasks are independent of the levels of Li or Lo, but correspond to the automata that can solve the corresponding transduction tasks. For example, for the reverse string task, Li equals Lo equals AB, both regular. However, learning the function f that maps WLI to reverse WLO requires a deterministic pushdown transducer, thus rendering the task deterministic context-free. Architectures. We consider a wide range of neural network architectures, including both state-of-the-art and memory-augmented models. Our goal is to have at least one model per level of the Chomsky hierarchy. To that end, we use a standard RNN as a controller and augment it with two kinds of differentiable memory structures, a deterministic stack and a bounded tape. The stack and tape have elements in RD with D equals 8, and we ensure that the stack and tape sizes are large enough to simulate infinite memory during training and testing. The stack RNN can perform any linear combination of push, pop, and no op operations on the stack. The tape RNN can perform any linear combination of right-left, right-right, right-stay, jump right, jump left. In addition to these memory-augmented models, we also evaluate LSTMs and transformers. We compute the transformer output from the encoder-only model that overlooks the whole input sequence. We consider 5 different positional encodings: none, classical SYN-COS, the rotary positional encodings, ALEB, and the relative positional encodings of transformer XL. All models receive the tokens X as an input and are expected to produce the output Y. We study CNNs, stack LSTMs, ND stack RNNs, and autoregressive versions of our models. Published as a conference paper at ICLR 2023. Score in percentage, i.e. accuracy averaged over all test lengths and maximized over 10 random seeds. We consider a model to generalize successfully if its score is at least 90%. The random accuracy is 50%, except for cycle navigation, bucket sort, and the two modular arithmetic tasks where it is 20%. We observe that, in general, RNNs with more permissive memory structures can solve more challenging tasks. We denote permutation invariant tasks with the, counting tasks with twith, tasks requiring a non-deterministic controller with the, and tasks requiring superlinear running time with tex. Level task RNN, stack RNN, tape RNN, transformer LSTM, Reven pairs 100.0, 100.0, 96.400. Modular arithmetic, simple, 100.0, 100.0, 100.0, 24.2, 100.0. Parity check 100.0, 100.0, 100.0, 52.0, 100.0. Cycle navigation 100.0, 100.0, 100.0, 61.9, 100.0. DCF stack manipulation 56.0, 100.0, 100.0, 57.5, 59.1. Reverse string 62.0, 100.0, 100.0, 62.3, 60.9. Modular arithmetic 41.3, 96.1, 95.4, 32.5, 59.2. Solve equation 51.0, 56.2, 64.4, 25.7, 67.8. CS duplicate string 50.3, 52.100, 52.8, 57.6. Missing duplicate 52.3, 55.100, 56.4, 54.3. Odds first 51.0, 51.9, 52.8, 55.6. Binary addition 50.3, 52.7, 100, 54.3, 55.5. Binary multiplication 50.0, 52.7, 58.2, 53.1. Compute score 56.5, 57.8, 54, 57.5. Bucket sort 27.99, 70.7, 91.9, 99.3. Data generation. Instead of using fixed-size datasets, we define training and test distributions from which we continually sample sequences. We define the maximum training sequence length as the training range n, with n equals 40. Every mini-batch is generated by first sampling a length data from the uniform distribution U1n, and then sampling sequences of length data from the task's generative grammar. For testing, we sample the sequence length data from UM plus 1m, with m equals 500. We provide an open-source implementation of our models, tasks, and training and evaluation suite at a GitHub link. Results. In this section, we provide the results of our empirical evaluation. In Section 5.1, we relate the networks to the Chomsky hierarchy. In Section 5.2, we analyze the algorithms learned by the networks. And in Sections 5.3 and 5.4, we discuss the performance of LSTMs and transformers in more detail. Published as a conference paper at ICLR. Internal RNN states on parity check, colored by the previous state and the current input. Probability of stack action per input token. Stack depth. Stack evolution for an input sequence. Stack RNN action probabilities above and stack values below on the modular arithmetic task. Action probabilities. Time step actions, right stay, right left, jump left. Memory index. Memory contents. Cell content. Tape RNN action probabilities and memory values on duplicate string. Main result, we evaluate all architectures on all tasks and show the generalization accuracy averaged over the segment in Table 2. Furthermore, displays the accuracy per sequence length for the best performing model per architecture on 3 sample tasks. We can gauge whether the architectures can learn the algorithm. The networks generally match the computational models associated with the Chomsky hierarchy. RNNs can solve tasks up to the regular level, stack RNNs up to the DCF level, and tape RNNs up to the CS level. However, the match is not perfect. For example, stack RNN cannot solve equation DCF, and the tape RNN cannot solve the binary multiplication and compute scort tasks. Some architectures show non-trivial performance on tasks beyond their supposed level. Transformers and LSTMs are not well aligned with the Chomsky hierarchy. Analysis of learned program structure. To provide evidence supporting the claim that some networks can learn the right algorithm, we provide an analysis of solutions learned by some networks on tasks, investigating internal state representations and memory update dynamics for regular tasks. We expect networks that solve regular tasks to simulate a finite-state automaton. We observe that the states form clusters, each representing one of the four values of the tuple. Due to the problem symmetry, the network also learns to compute the parity of the number of zeros in the string. We also investigate whether and how stack RNNs use their published as a conference paper at ICLR 2023 stack for this task, which is unnecessary in principle. Indeed, the stack RNNs only use no op or pop, which is equivalent to no op in the absence of push actions, indicating that the RNN controller uses only a finite-state automaton and does not rely on the stack. Deterministic context-free tasks. On DCF tasks, we anticipate stack RNNs to use their stack. Indeed, on reverse string DCF, the networks learn the expected algorithm, push until an empty token appears, and then pop until the stack is empty. Moreover, the internal state of the controller seems to be largely guided by the last input token and not the last state. On modular arithmetic, DCF, which requires a stack to remember past results when entering a new bracket, the networks use the stack exactly as expected. Figure 3b shows that the stack RNN learns to solve this task by I. Pushing the last result when a bracket is opened, T. Not operating on the stack and only using its internal controller when a number or an operator is seen, and T. Popping the last result from the stack when a bracket is closed. The top plot reports the probability of each action given an input, and the bottom plot shows the stack evolution along the sequence. On the bottom plot, the x-axis is the time step, and the y-axis is the cell position in the stack, top of the stack on the bottom. Each cell is colored according to the first principal component of its actual content. Context-sensitive tasks. In contrast to the RNN and stack RNN, the reverse-engineered network mechanisms for the tape RNN are less interpretable. Nevertheless, Fig 3c shows that the tape RNN has learned an algorithm that is indicative of the data-generating grammar of the duplicate string CS task. The input to the network consists of the sequence A, B, A of length L equals 4, followed by 2L alpha symbols that the RNN can use to compute and manipulate the tape, followed by 2L beta symbols used to output the result, i.e. the sequence A, B, A of length 2L. The panels show the action probabilities and memory contents over time. We observe that up to time t equals 5, the RNN writes on the memory with W write left. Then, on time step 6, the RNN mixes jump right and write stay to duplicate the input string in the memory, before moving back to the initial position with jump right on time step 7. After this, the RNN idles using write stay until it reaches the first beta symbol, whereupon it starts outputting the result using write left actions. LSTMs. LSTMs are similar to RNNs as they also carry a hidden state and are unrolled over a sequence of inputs. However, prior work showed that LSTMs are strictly more powerful than RNNs because they can also solve counting tasks. Indeed, Table 2 provides further evidence for this claim since LSTMs are capable of solving bucket sort CS almost perfectly, even though the task is context sensitive. That is, counting tasks can reside on levels higher than regular in the Chomsky hierarchy, since every Turing machine can, in theory, be simulated by a two-counter machine. However, finding an architecture that solves non-regular tasks with counters via gradient descent is more difficult than when the controller has access to a more permissive memory structure, such as a stack or a tape. Transformers. Unlike the other architectures, transformers are permutation invariant WT the position of a token in a sequence because they rely on a global attention mechanism. As a result, transformers are more scalable since all tokens can be processed in parallel, however, at the cost of reduced expressivity, i.e., permutation invariance. Similar to real-world problems, most of our tasks are not permutation invariant, e.g., reversing a string depends on the token's position. To overcome this problem, transformers are generally augmented with positional encodings, which are added to the tokens to simulate some notion of position. Consequently, the augmented tokens intrinsically contain position information, i.e., the token X at position 0 will no longer be considered the same as the same token X at position 10. As described in Section 4, we evaluate 5 encodings, none, sin, cos, relepe, and the relative positional encoding from transformer XL, and report the best performing variant. Indeed, Table 2 shows that transformers are most successful on permutation invariant tasks. They solve bucket sort, CS, and demonstrate non-trivial generalization on cycle navigation, R. Moreover, they solve even pairs, R, which is not permutation invariant but only requires checking whether the first and last tokens are equal. However, for all other tasks, transformers fail to generalize, regardless of their positional encodings. Published as a conference paper at ICLR 2023, Sequence Length Accuracy None. Original Sin Cos I Transformer XL Rope, Accuracy per Length by Positional Encoding. First Layer Activations by Sequence Length. Transformers on Reverse String. Without positional encodings, transformers are permutation invariant, and with encodings, positions are out of distribution for longer sequences. Different positional encodings on reverse string and for the remaining tasks. In particular, transformers are unable to solve all permutation invariant tasks, which is a well-known failure mode. We hypothesize that this poor performance is due to the positional encodings, which take on new values when the sequences grow longer, meaning that the network activations will be out of distribution. Indeed, shows that the 2D PCA of the first layer activations is similar for sequences of length 40 and 50, but completely different for length 150. All our other models, which do not rely on global self-attention, do not suffer from this effect, as they only have access to a local view of the input token. Discussion. In this paper, we considered generalization from a sequence prediction viewpoint, using formal language theory to establish the computational complexity of each task. Naturally, we had to choose a maximum test sequence length for our evaluations, which theoretically renders all of our input and output languages finite. However, our sequences share the structure of an infinite language, allowing us to measure generalization by testing on input sequences that are significantly longer than those seen during training. Therefore, observing successful generalization in our setting is strong evidence that the network has learned the correct algorithm. However, for some tasks where we consider generalization to be successful, we still see a slight degradation of the accuracy as the test length increases. This is a result of implementing finite state machines and memory updates with a neural network trained via SGD. Even slight numerical inaccuracies in state transitions or memory dynamics might accumulate when increasing the test sequence length. Our experiments indicate that RNNs, LSTMs, and transformers, admittedly powerful architectures, are fairly limited in terms of their ability to generalize to longer inputs. However, this result must be contrasted with their ability to generalize and detect/extrapolate patterns for fixed-size inputs or fixed-size context windows. Transformers, for instance, are capable of learning complex and highly structured generalization patterns, but they cannot overcome the limitation of not having an extendable memory. This might imply hard limits for scaling laws. Even significantly increasing the amount of training data and the size of a transformer are insufficient for it to climb the Chomsky hierarchy. Conclusion. We leverage the theory of computation to better understand how and why neural networks generalize on algorithmic sequence prediction tasks. Our extensive empirical evaluation demonstrates that there is a model hierarchy on the tasks we investigated, which are representative of the different levels of the Chomsky hierarchy. In particular, we showed that state-of-the-art architectures, such as LSTMs and transformers, cannot solve seemingly simple tasks, such as duplicating a string, when evaluated on sequences that are significantly longer than those seen during training. Moreover, we showed that models interacting with an external memory structure, such as a stack or a finite tape, can climb the Chomsky hierarchy, indicating a promising direction for improvements in architecture design. Although our results are consistent with prior theoretical analyses and suggest that we can group neural architectures according to the Chomsky hierarchy, our claims are limited to our empirical study. In particular, we cannot guarantee that no tasks exist higher in the hierarchy that an architecture could solve. Similarly, we cannot guarantee that no tasks exist lower or on the same level of the hierarchy that an architecture cannot solve. Moreover, without extracting and analyzing the automata implemented by the networks, we cannot strictly claim that our architectures generalize to arbitrary length inputs, as we only test up to a maximum length. Finally, our results are with respect to our precise experimental setting. That is, if an architecture fails to generalize, We cannot guarantee that no weight configuration would solve the task. We were simply unable to find such a configuration with our training protocol. Published as a conference paper at ICLR 2023, James Bradbury, Roy Frostig, Peter Hawkins, Matthew James Johnson, Chris Leary, Dougal McLaurin, George Nicola, Adam Pasca, Jake Vanderplas, Sky Wanderman Milne, and Qiao Zhang. JAX, Composable Transformations of Python's NumPy Programs, 2018. Yining Chen, Sorcha Gilroy, Andreas Maletti, Jonathan May, and Kevin Knight. Recurrent Neural Networks as Weighted Language Recognizers. In proceedings of the 2018 conference of the North American chapter of the Association for Computational Linguistics, Human Language Technologies, 2018, David Chang and Peter Chalak, Overcoming a Theoretical Limitation of Self-Attention, 2022. Kyunghyun Cho, Bart van Marienboer, Chaglar Gulchera, Dmitry Bogdanov, Fethi Bugaris, Holger Schwenk, and Yoshua Bengio. Learning phrase representations using RNN encoder-decoder for statistical machine translation. In proceedings of the 2014 Conference on Empirical Methods in Natural Language Processing, 2014, Noam Chomsky, Three Models for the Description of Language, IR Trans, Inf Theory, 1956. Zihang Dai, Jilin Yang, Yiming Yang, Jamie G. Carbonell, Kwok-Viet Le, and Ruslan Salakutdinov. Transformer XL, Attentive Language Models Beyond a Fixed-Length Context. In proceedings of the 57th Conference of the Association for Computational Linguistics, 2019, Ivo Danihelka, Greg Wayne, Benigno Uria, Nal Kalchbrenner, and Alex Graves. Associative Long Short-Term Memory. In proceedings of the 33rd International Conference on Machine Learning, 2016, Srirupa Das, C. Lee Giles, and Guozheng Sun. Learning Context-Free Grammars. Capabilities and limitations of a recurrent neural network with an external stack memory. In 14th Annual Conference of the Cognitive Science Society, 1992, Srirupa Das, C. Lee Giles, and Guozheng Sun, using prior knowledge in a NNPDA to learn context-free languages. In Advances in Neural Information Processing Systems 5, 1992, A. Philip Dawood. Present Position and Potential Developments, Some Personal Views, Statistical Theory, The Prequential Approach, Journal of the Royal Statistical Society, Series A, General, 1984. Brian Dussel and David Chiang, Learning Context-Free Languages with Non-Deterministic Stack RNNs, in proceedings of the 24th Conference on Computational Natural Language Learning, 2020. Brian Dussel and David Chiang, Learning Hierarchical Structures with Differentiable Non-Deterministic Stacks. In the 10th International Conference on Learning Representations, 2022, Javed Ebrahimi, Dhruv Gelda, and Wei Zhang. How can self-attention networks recognize DAC-N languages? In findings of the Association for Computational Linguistics, 2020. Jeffrey L. Ellman, Finding Structure in Time, CognosCI, 1990. Carlos Freivalds and Renars Liepens, Improving the Neural GPU Architecture for Algorithm Learning, CoRR, 2017. Felix A. Gers and Jürgen Schmidhuber. LSTM recurrent networks learn simple context-free and context-sensitive languages. ITRI Trans, Neural Networks, 2001. C. Lee Giles, Clifford B. Miller, Dong Chen, Xinghen Chen, Guozheng Sun, and Yichun Li. Learning and extracting finite-state automata with second-order recurrent neural networks. Neural Compute, 1992. David E. Goldberg, Genetic Algorithms in Search Optimization and Machine Learning. Addison Wesley, 1989, Faustino J. Gomez, Jürgen Schmidhuber, and Risto Mikulainen. Accelerated Neural Evolution Through Cooperatively Co-Evolved Synapses. J. Mach Learn Res, 2008. Published as a conference paper at ICLR 2023, Alex Graves. Adaptive Computation Time for Recurrent Neural Networks. CoR, 2016. Alex Graves, Greg Wayne, and Ivo Danihelka, Neural Turing Machines. CoR, 2014. Alex Graves, Greg Wayne, Malcolm Reynolds, Tim Harley, Ivo Danihelka, Agnieszka Grabska-Barwinska, Sergio Gomez-Colmenarejo, Edward Greffenstedt, Tiago Ramallo, John P. Agapio, Adria Pugdamanich-Badia, Carl Moritz Herman, Joris Wolz, Georg Ostrovsky, Adam Kane, Helen King, Christopher Summerfield, Phil Blunsum, Kore Kavakcioglu, and Demis Hassabis. Hybrid computing using a neural network with dynamic external memory. NAT 2016. Edward Greffenstedt, Carl Moritz Herman, Mustafa Suleiman, and Phil Blunsum. Learning to Transduce with Unbounded Memory. In Advances in Neural Information Processing Systems 28, 2015. Chaglar Gulchere, Sarath Chandar, Kyunghyun Cho, and Yoshua Bengio. Dynamic Neural Turing Machine with Continuous and Discrete Addressing Schemes. Neural Compute 2018. Michael Hahn. Theoretical Limitations of Self-Attention in Neural Sequence Models. Trans-ASOC Compute Linguistics 2020. Yiding Hao, William Merrill, Dana Angluin, Robert Frank, Noah Amsel, Andrew Benz, and Simon Mendelssohn. Context-free transductions with neural stacks. In Proceedings of the Workshop, Analyzing and Interpreting Neural Networks for NLP 2018. Yiding Hao, Dana Angluin, and Robert Frank. Formal Language Recognition by Hard Attention Transformers, Perspectives from Circuit Complexity. COAR 2022. Tom Hennigan, Trevor Kai, Tamara Norman, and Igor Babushkin. Haiku, Sonnet for Jax 2020. Matteo Hessel, David Budden, Fabio Viola, Mihaela Roska, Aaron Cezanner, and Tom Hennigan. Optax, Composable Gradient Transformation and Optimization in JAX 2020. Sepp Hochreiter and Jürgen Schmidhuber. Long Short-Term Memory, Neural Compute 1997. John H. Holland, Adaptation in Natural and Artificial Systems, an Introductory Analysis with Applications to Biology, Control, and Artificial Intelligence. MIT Press, 1992. Stefan Hull-Dobler, Yvonne Kalinke, and Helko Lehmann. Designing a Counter, another case study of dynamics and activation landscapes in recurrent networks. In Advances in Artificial Intelligence, 21st Annual German Conference on Artificial Intelligence, 1997. Armin Julin and Thomas Mikolov, Inferring Algorithmic Patterns with Stack-Augmented Recurrent Nets. In Advances in Neural Information Processing Systems, 2015. Lukas Kaiser and Ilya Sutskever, Neural GPUs Learn Algorithms. In 4th International Conference on Learning Representatives 2016, Nal Kalchbrenner, Ivo Danihelka, and Alex Graves. Grid Long Short-Term Memory. In 4th International Conference on Learning Representations 2016, Jared Kaplan, Sam McCandlish, Tom Hennigan, Tom B. Brown, Benjamin Chess, Riwon Child, Scott Gray, Alec Radford, Jeffrey Wu, and Dario Amode. Scaling Laws for Neural Language Models. COAR 2020. Diederik P. Kingma and Jimmy Ba. Atom, A Method for Stochastic Optimization. In 3rd International Conference on Learning Representations 2015. Samuel A. Korsky and Robert C. Berwick. On the Computational Power of RNNs. COAR 2019. Karl Kuruk, Marcin Andrikowicz, and Ilya Sutskever. Neural Random Access Machines. In 4th International Conference on Learning Representations 2016. Published as a conference paper at ICLR 2023, Percy Lang, Michael I. Jordan, and Dan Klein. Learning Dependency-Based Compositional Semantics, Compute Linguistics 2013. Ankur Arjun Mali, Alexander Ororbia, Daniel Kiefer, and C. Lee Giles. Recognizing long grammatical sequences using recurrent networks augmented with an external differentiable stack. In Proceedings of the 15th International Conference on Grammatical Inference, 2021. William Merrill, Sequential Neural Networks as Automata, COAR 2019. William Merrill and Ashish Sabharwal. Log Precision Transformers are Constant Depth Uniform Threshold Circuits, COAR 2022. William Merrill, Gail Weiss, Yoav Goldberg, Roy Schwartz, Noé Smith, and Aaron Yahav. A Formal Hierarchy of RNN Architectures. In Proceedings of the 58th Annual Meeting of the Association for Computational Linguistics 2020. Marvin L. Minsky. Computation, Finite and Infinite Machines, Prentice Hall, Inc., 1967. Tom M. Mitchell, The Need for Biases in Learning Generalizations, Technical Report, Rutgers University, 1980. Michael Moser and Srirupa Das, A Connectionist Symbol Manipulator that Discovers the Structure of Context-Free Languages, in Advances in Neural Information Processing Systems 5, 1992. Peter Norden, Evolutionary Program Induction of Binary Machine Code and Its Applications, PhD thesis, Dortmund University of Technology, 1997. Jorge Perez, Javier Marinkovic, and Pablo Barceló, On the Turing Completeness of Modern Neural Network Architectures, in 7th International Conference on Learning Representations, 2019. Jorge Perez, Pablo Barceló, and Javier Marinkovic. Attention is Turing Complete. JMOC Learn Res, 2021. Jordan B. Pollack, The Induction of Dynamical Recognizers. Mock Learn, 1991. Alithia Power, Yuri Burda, Harrison Edwards, Igor Babushkin, and Vedant Misra. Grokking, Generalization Beyond Overfitting on Small Algorithmic Datasets, COAR 2022. Ofer Press, Noah A. Smith, and Mike Lewis. Train Short, Test Long, Attention with Linear Biases Enables Input Length Extrapolation, COAR 2021. Eric Price, Wojciech Zaremba, and Ilya Sutskever. Extensions and Limitations of the Neural GPU. CoRR 2016, Elaine Rich. Automata, Computability and Complexity, Prentice Hall, 2007. Paul Rodriguez and Janet Wiles. Recurrent neural networks can learn to implement symbol-sensitive counting. In Advances in Neural Information Processing Systems 10, 1997. John E. Savage, Models of Computation, Exploring the Power of Computing, Addison Wesley, 1998. Lucy Sennhauser and Robert C. Berwick, Evaluating the Ability of LSTMs to Learn Context-Free Grammars. In Proceedings of the Workshop, Analyzing and Interpreting Neural Networks for NLP, 2018. Hava T. Siegelman, Eduardo D. Sontag, Analog Computation via Neural Networks, Theor Compute Sci, 1994. Michael Sipser, Introduction to the Theory of Computation, PWS Publishing Company, 1997. Natalia Skachkova, Thomas Alexander Trost, and Dietrich Klakow. Closing brackets with Recurrent Neural Networks. In Proceedings of the Workshop, Analyzing and Interpreting Neural Networks for NLP, 2018. Ray J. Solomonoff, A Formal Theory of Inductive Inference, Part 1, Inf Control, 1964a. Ray J. Solomonoff, A Formal Theory of Inductive Inference, Part 2, Information Control, 1964b. Ray J. Solomonoff, Algorithmic Probability, Theory and Applications, in Information Theory and Statistical Learning, Springer, U.S., 2009. Ray J. Solomonoff, Algorithmic Probability, Heuristic Programming in AGI, in Proceedings of the 3D Conference on Artificial General Intelligence, 2010. Mark Stivers and Peter Grunwald, A Recurrent Network that Performs a Context-Sensitive Prediction Task, in 18th Annual Conference of the Cognitive Science Society, 1996. John Stogan, Ankur Arjun Mali, and C. Lee Giles, Provably Stable Interpretable Encodings of Context-Free Grammars in RNNs with a Differentiable Stack, 2020. Jianlin Su, Yulu, Shengfeng Pan, Bo Wen, and Yunfeng Liu. Roformer, Enhanced Transformer with Rotary Position Embedding, 2021. Sainbayar Sukbadar, Arthur Slam, Jason Weston, and Rob Fergus. End-to-End Memory Networks, in Advances in Neural Information Processing Systems, 28, 2015. GZ Sun, CL Giles, HH Chen, and YC Lee. The Neural Network Pushdown Automaton, Model, Stack, and Learning Simulations. Technical Report, University of Maryland, 1993. Ilya Sutskever, Oriol Vinyals, and Quo V. Lee. Sequence-to-Sequence Learning with Neural Networks, in Advances in Neural Information Processing Systems 27, 2014. Murak Suzgun, Sebastian German, Jonathan Belinkov, and Stuart M. Schieber. LSTM networks can perform dynamic counting, CoRR 29a. Murak Suzgun, Sebastian German, Jonathan Belinkov, and Stuart M. Schieber. Memory-augmented recurrent neural networks can learn generalized Dyke languages, CoRR 29b. Vladimir Vapnik. Statistical Learning Theory, Wiley, 1998. Ashish Vaswani, Noam Shazir, Niki Parmar, Jacob Buskorite, Lion Jones, Aidan N. Gomez, Lukas Kaiser, and Ilya Polasukin. Attention is all you need. In Advances in Neural Information Processing Systems 30, 2017. Gail Weiss, Yoav Goldberg, and Eran Yahav. On the Practical Computational Power of Finite Precision RNNs for Language Recognition, in Proceedings of the 56th Annual Meeting of the Association for Computational Linguistics 2018. Gail Weiss, Yoav Goldberg, and Eran Yahav. Thinking Like Transformers, in Proceedings of the 38th International Conference on Machine Learning 2021. Jason Weston, Sumit Chopra, and Antoine Bordes. Memory Networks, in Third International Conference on Learning Representations 2015. Janet Wiles and Jeff Ellman. Learning to Count Without a Counter, a case study of dynamics and activation landscapes in recurrent networks. In 17th Annual Conference of the Cognitive Science Society, 1995. Mark Weinberg and Franz Opacher. A representation scheme to perform program induction in a canonical genetic algorithm. In Parallel Problem Solving from Nature, PPSN 3, International Conference on Evolutionary Computation, 1994. Greg Yang and Alexander M. Rush. Lie-Access Neural Turing Machines. In 5th International Conference on Learning Representations, 2017. Danny Yogatama, Yishu Miao, Gabor Melis, Wang Ling, Adiguna Kunkoro, Chris Dyer, and Phil Blunsum. Memory Architectures in Recurrent Neural Network Language Models. In 6th International Conference on Learning Representations 2018, Wojciech Zaremba and Ilya Sutskever. Reinforcement Learning Neural Turing Machines, CoRR 2015. Published as a conference paper at ICLR 2023, Wojciech Zaremba, Tomas Mikolov, Armand Julin, and Rob Fergus. Learning simple algorithms from examples. In Proceedings of the 33rd International Conference on Machine Learning, 2016, Yi Zhang, Arturs Bakhurs, Sebastian Bubek, Ronan Eldon, Surya Gunasakar, and Tal Wagner. Unveiling Transformers with Lego, a Synthetic Reasoning Task, COAR 2022. Published as a conference paper at ICLR 2023, Experimental Details, Language Recognition vs. Transduction. In practice, learning to recognize a formal language by training a classifier on words and non-words of a language is hard because there is, in general, no formal construction for generating a sufficient but finite set of negative examples. Thus, prior work has relied on other approaches to evaluate language recognition capabilities. These approaches are variants of language generation, which are as hard as their recognition counterpart for a given language, and thus are good proxy tasks. The first approach is autoregressive token prediction, standard in the machine learning community. Given a prefix P of a word WL, predict the probability of its next token T. The main problem with this approach is that the probabilities depend on the length distribution of the training strings. For instance, for the language of palindromes of length 2, with alphabet equals A, B, the output probabilities are P, A prefix equals A equals 1 and B prefix B equals 1. However, for palindromes of length 3, the probabilities are very different, i.e. PA prefix equals A equals 0.5 and PB prefix B equal 0.5. Therefore, there is a conflict between the different distributions, and no model can solve the task without knowing the length beforehand. Accordingly, increasing the length at test time without informing the model makes it impossible to find the correct new probabilities and, therefore, to generalize to inputs of unseen lengths. The second approach is to predict the set of possible next tokens and not their probabilities. In this case, the distribution of possible next tokens does not change with the length, and increasing the length at test time is possible. However, for each prefix, the target will consist of a set of tokens, which is incompatible with the prediction setting and thus of lesser interest to the wider machine learning community. Our approach is similar to the second one, but we only consider prefixes for which there is only one possible, deterministic continuation. Thus, instead of language generation, we consider language transduction. The inputs and outputs form two individual languages, and the goal is to learn the deterministic function that maps a word from one to the other. The automata solving these tasks are the classical automata, but with outputs attached to each transition and are denoted transducers. Therefore, the hierarchy that we consider is a hierarchy over transducers and not over acceptors, as detailed in Section 3. However, the two types of machines are interchangeable for the purposes of our investigation, as they are both memory-augmented finite-state automata that reside on different levels of the Chomsky hierarchy depending on their type of external memory access: none, a stack, or a tape. Models. Here we describe our neural architectures in more detail. All models have a final linear readout layer to produce the output logits. We do not use any regularization, for example, weight decay dropout, except for the transformer models. For training of the memory-augmented models, we set the tape size to 256 and the stack size to 128, and manually increase their sizes when testing on longer sequences. Thus, as these memory sizes are significantly larger than the training range n, the finite memory models appear infinite for our neural architectures in the context of our experimental evaluation. Moreover, increasing the memory size does not affect how the RNN controller takes actions, since it only has access to a local view of the external memory, e.g., the top of the stack or the current memory cell. RNN a vanilla single-layer RNN with hidden size of 256. Stack RNN a single-layer RNN controller of hidden size 256 with access to a differentiable stack. The controller can perform any linear combination of push, pop, and no-op on the stack, with action weights given by a softmax over a linear readout of the RNN output. Each cell of the stack contains a real vector of dimension 8. ND-stack RNN, a single-layer RNN controller of hidden size 256 with access to a differentiable non-deterministic stack. We consider the ND-stack RNN proposed by, which simulates a non-deterministic stack via dynamic programming. Concretely, we use Normalized 16, published as a conference paper at ICLR 2023, actions and non-deterministic state reading with two states and sweep over 4 symbols. We did not use the unnormalized actions as suggested in Dussel and Chiang 2022. Tape RNN, a single-layer RNN controller of hidden size 256 with access to a differentiable tape, inspired by the baby NTM architecture, Suzgan et al. 29b. The controller can perform any linear combination of right-right, right-left, right-stay, jump left, and jump right on the tape, with action weights given by a softmax. The actions correspond to writing at the current position and moving to the right, right-right, writing at the current position and moving to the left, right-left, writing at the current position, right-stay, jumping T steps to the right without writing, jump right, where T is the length of the input, and jumping J steps to the left without writing, jump left. Finally, to allow the tape RNN to perform memory operations without having to produce the output, we append computation tokens, different from the empty tokens that, used to produce the output, see Appendix 8.4 below, to the input sequence. As in the stack RNN, each cell of the tape contains a real vector of dimension 8. LSTM, a vanilla single-layer LSTM Hochreiter and Schmidhuber, 1997, of hidden size 256. Stack LSTM, a single-layer LSTM controller of hidden size 256 with access to a differentiable stack Julin Mikolov, 2015. The only difference to the stack RNN is that this model uses an LSTM as the controller. Transformer encoder, a vanilla transformer encoder, Vaswani et al., 2017. We do not use the autoregressive sequence-to-sequence model to produce the output, but attend the whole input, including the empty tokens train. We use 5 blocks with D model equals 64, where each block is composed of an attention layer, 2 dense layers, and a layer normalization. We add a residual connections as in the original architecture, Vaswani et al., 2017. We consider 5 different positional encodings: none, classical Sin-Cos, Vaswani et al., 2017, Rope, Su et al., 2021, Al, Press et al., 2021, and the relative positional encoding from Transformer XL, Dai et al., 2019. Transformer, autoregressive, a vanilla transformer, Vaswani et al., 2017. We do not use empty tokens TAD anymore, and the output is produced via the decoder, using causal masking. We use the same hyperparameters and positional encodings as for the transformer encoder above. Convolutional neural network, a vanilla CNN, consisting of 5 convolutional layers with 32 channels each and a final MLP that produces the task outputs. We compute 2D convolutions over the time and one-hot encoding channel dimension. That is, the first kernel will consider the entire one-hot encoding at once for every time step. For all other kernel dimensions, time and filters, we sweep over the values 3, 5, 7, 11. Tasks. Here we describe our tasks, listed in Table 8.1, in more detail. As mentioned in Section 4, all tasks consist of an input sequence XLI, from which the models have to predict the target sequence YLO. We append Y empty tokens braid to the input sequence, such that the models can process the entire input sequence before having to produce the output, i.e., they know the input length before having to produce the output. Note that half of our tasks have an output length of 1, and are thus just standard classification tasks, with the set of classes being the alphabet of the output language. The networks still see one empty token 2 at the end of the input string to signify that the input phase has finished and that the output must be computed. We do not consider NDCF tasks since the distinction between DCF and NDCF is fairly technical and does not fundamentally change the type of memory structure required, i.e. a stack. Even pairs are, given a binary sequence, e.g. x equals a-ba, compute if the number of abs and bas is even. For a-ba, we have 1 ab and ba, meaning that the total number is 2, and thus even, i.e. y equals b, where we arbitrarily equate odd with a and even with b. This task is equivalent to computing whether the first and last character of the string are equal. Therefore, the task is regular since we can solve it with a 2-state finite state machine that looks at the first bit of the sequence and compares it with the last one. Published as a conference paper at ICLR 2023, Modular Arithmetic Simple. Given a sequence of numbers in 0, 1, 2, 3, 4, and operations in ±5, compute the result modulo 5. For example, x equals 1 plus 2 minus 4 evaluates to y equals 4. Note that the length of the input sequences must be odd. Therefore, if we sample an even length during the training evaluation process, we return an input sequence of this length plus 1. This task is regular since we can solve it with a 5-state finite state machine, which transitions for each new operation with the state being equal to the current result. Parity check. Given a binary string, e.g. a, compute if the number of bs is even. The sequence x equals aaba contains 2 bs, which is even, i.e. y equals b, where we arbitrarily equate odd with a and even with b. This task is regular since we can solve it with a 2-state finite state machine, which transitions every time it sees a token different from its current state. Cycle navigation. Given a sequence of movements on a cycle of length 5, compute the end position. The movements are stay, increase, decrease, and are represented as 0, 1, 2. The agent always starts at position 0. For example, 0, 1, 0, 2, 1, 1 means the agent stops at position 0 plus 0 plus 1 plus 0 minus 1 plus 1 equals 2, and the output class is 2. This task is regular since we can solve it with a 5-state finite state machine, similar to modular arithmetic, simple, as the task can be converted into a sum modulo 5. Modular arithmetic DCF. Given a sequence of numbers in 0, 1, 2, 3, 4, brackets, and operations in plus, minus, k, compute the result modulo 5. For example, the sequence x equals minus 1 minus 2, 4 minus 3 minus 2 evaluates to y equals 0. Note that we do not have the same problem of odd lengths as in modular arithmetic, simple, since we can use substrings of the form MIGA z with z 0, 1, 2, 3, 4, which have length 4 and thus can be used to produce input strings of even length. The task is DCF since we can solve it with a 5-state finite state machine and an external stack. That is, similar to the modular arithmetic simple task, the finite state machine transitions for each new operation, with the state being equal to the current result. Moreover, the stack is used to handle brackets. The machine pushes if the current input token is an opening bracket, pops if it is a closing bracket, and uses no ops to let the finite state machine work otherwise. Reverse string DCF. Given a binary string, e.g. x equals aaba, compute its reverse, i.e. y equals aba. The task is DCF since we can solve it by pushing the tokens of the input sequence on a stack until the first empty token dot appears, and then popping the tokens from the stack, outputting the values one by one. This task cannot be solved with a finite state machine since the number of possible outputs is infinite. Solve equation DCF. Given an equation consisting of numbers in 0, 1, 2, 3, 4, brackets, operations in plus, minus, minus, and an unknown variable z, compute the value of z such that the equation holds modulo 5. For example, x equals minus z minus 2, 4 minus 3 minus 2 equals 0 modulo 5 holds for z equals 1, i.e. y equals 1. This task is DCF since we can solve it by simulating all possible values of x in a non-deterministic finite state machine and producing each result using the same algorithm as in modular arithmetic, DCF. Note that a non-deterministic finite state machine can be simulated with a deterministic one, implying that this task is DCF and not NDCF. Stack manipulation, DCF. Given a binary string representing a stack's content, given bottom to top, and a sequence of push A, push B, or pop actions, execute the actions on the stack and return the final stack content in a top-to-bottom manner, i.e., as if popping the resulting stack. For example, executing the sequence pop push A pop on the stack above, i.e. x equals a pop push A pop, results in y equals above. If a pop action is called on an empty stack, the action is ignored. This task requires stack manipulation by design and is therefore DCF. Binary addition, CS. Given two binary numbers, e.g. 10 and 101, compute their sum in base 2, i.e. y equals 1011 for x equals 1n plus 101. The inputs and outputs are given in little endian representation. The task is CS since it exhibits cross-serial dependencies because the two numbers are provided one after the other and not bit by bit at the same time. Binary multiplication, CS. Given two binary numbers, e.g. 100 and 111, compute their product in base 2, i.e. y equals 1110 Zaur for x equals 100 and 111. The inputs and outputs are given in, published as a conference paper at ICLR 2023, are tasks with their level in the Chomsky hierarchy and example input-output pairs. The ZROD denotes permutation invariant tasks, the denotes counting tasks, the denotes tasks that require a non-deterministic controller, and the HEGS denotes tasks that require superlinear running time in terms of the input length. Level name example, input example, output. Riven pairs, AABA, true modular arithmetic, simple. 1 plus 2 minus 4 parity check. AABA, true cycle navigation, 011210 DCF stack manipulation, ABA-A. Pop push a pop ABA reverse string, ABA modular arithmetic. 9 is 1 minus 2, 4 minus 3, minus 2 equals 0. Solve equation, that is x minus 2, 4 minus 3, 2 equals 1. CS duplicate string, ABAB, ABA, BABA, missing duplicate, 1 on 2 1, odds first, ABA, binary addition, 1001 on plus 101 equals 1001 101. Binary multiplication, 1001 on once 101 equals 101 1000. Compute squirt, 1001 1 ton. Compute squirt CS. Given a binary number, e.g. 10101, compute the floor of its square root, i.e. y equals 1001 equals 101. The inputs and outputs are given in little endian representation. This task is CS since the digit-by-digit algorithms to compute the integer square root require many sequence manipulations, including binary multiplications, which is a CS task. Duplicate string, CS, given a binary string, e.g. x equals a, output the string twice, i.e. y equals a ababab. This task is CS since it corresponds to the well-known language WW is a word, CF section 3, which is CS. Missing duplicate, CS. The input is a binary string of the form WW, where W is itself a binary string. One token in this string has been hidden, and the network must find out which one it is by looking at the value at the same position but on the other side of the string. For instance, if x equals ABABA, i.e. W equals ABA, then y equals A. This task is CS since it relies on the recognition of the well-known language WW is a word, CF section 3, which is CS. Odds first CS. Given a binary string T1.tn, output T1 T5 4 T6. For example, the output corresponding to x equals a ba is y equals a ba. The task is CS because it exhibits cross-serial dependencies. The output is the interleaved input. Bucket sort CS. Given a string over an alphabet of fixed size 5 in our case, return the sorted string. Since the alphabet has a fixed size, the task can be solved via bucket sort, which only requires a finite amount of counters, i.e. 5 counters in our case. For example, the output corresponding to x equals 42130 is y equals 012222344. The task is CS because it requires multiple counters that keep track of the number of occurrences for every token. Published as a conference paper at ICLR 2023 Problem Setup. We now provide the full formalization of our problem setup. Algorithm illustrates our training procedure. We train on sequences of length that ranges from 1 to n, with n being 40, using batches of size 128. For testing, we consider sequences of length sampled from n to m, with m being 500. In general, we report the score, which we define as the per-sequence accuracy A averaged over all sequences of unseen length, i.e., score is the sum of A, x, y, as tie ranges from n plus 1 to m over m minus n. We use the atom optimizer with default hyperparameters for 1,000 steps, which we have found to be sufficient to achieve a near-optimal training performance for all tasks and architectures. As described in the algorithm, we augment our input sequences x with empty tokens t, where m is the length of the corresponding target sequence y, so that the networks only need to start outputting after they have consumed the entire input sequence. Moreover, we add computational tokens, different from the empty tokens y, to the input sequence x for the tape RNN to enable it to perform memory operations without having to output the result. In general, we run all experiments with 10 different random seeds used for network parameter initialization and 3 learning rates, 1 tub 10^-4, 3 cons 10^-4, and 5 10^-4, reporting the result obtained by the hyperparameters with the maximum score, means, and standard deviations in Appendix B. However, for transformers, NDStack RNNs, and tape RNNs, we sweep over additional hyperparameters. For transformers, we consider 5 different positional encodings. For NDStack RNN, we optionally read from internal states of the non-deterministic stack and sweep over 2 and 4 symbols. For the tape RNN, we consider different numbers of computation tokens, 0, t, or 2 that, and tapes, 1 and 4. Training pipeline for our sequence prediction tasks. The comments in blue show an example output for the reverse string DCF task. Input model p theta x with parameters theta, learning rate a, number of training steps, s initialize parameters th, sample length de from u140, sample sequence x of length t from the task's input grammar. Compute the corresponding output sequence y of length m. Pad x with m empty token stray such that the model only needs to start outputting after having consumed the entire input sequence. Set the output to an empty sequence of length m. Compute the output probability distribution O. Compute the cross-entropy loss, averaged over output tokens. C. Update the parameters with gradient descent theta. Compute the per-sequence accuracy. Computational resources. We implemented our evaluation suite in JAX using the DeepMind JAX ecosystem. We make all of our code publicly available at. We ran each task architecture hyperparameter triplet on a single TPU on our internal cluster. For RNNs, stack RNNs, LSTMs, and stack LSTMs, the hyperparameters we have used are learning rates and seeds, which gives 1800 TPU units. For tape RNNs, the hyperparameters we have used are the learning rate, the number of computation steps, the number of tapes, and the random seeds, which yields 2700 TPU units. For transformers, encoder, and autoregressive, the hyperparameters we have used are the learning rate, the positional encodings, and the random seeds, which gives 4,500 TPU units. Published as a conference paper at ICLR 2023. Mean and standard deviation of the running times for all architectures and tasks. The SA indicates permutation invariant tasks, indicates counting tasks, indicates tasks that require a non-deterministic controller, and TEX indicates tasks that were superlinear running time in terms of the input length. Level task, RNN, stack RNN, ND stack RNN, tape RNN, transformer LSTM, stack LSTM autoreg. Transformer Reven pairs 037.1.56 to 4.01, 8.5.16, 3.preuse 2.1, 1.19.73, 7.5, 0.03, 2.97, 0.01, 1.61.27. Modular arithmetic simple. 0.57, 0.92.06, 8.06, 2.48, 1.31 muz 0.55 and 6.0.62 dozo 3.05 3 narrow of f.01 224. Parity check 0.59 reward do deviate sibarat 280 beto 58 0 1 37 is 2.3 do 1.2 relay bank 6 no 6 2.96 0 101.61 0.27 cycle. Navigation 0.60 pi 0 no 3.57 0 no 7 8.42.233.212.2 time 0.66 7 is 2 do through 2.9760 0.01045. DCF stack manipulation 4.07011 4.69 to 8 6.80 down 1.43 8.27 to 2.93 5.06 to 0.65 4.27 0.108 0.47 2.25 minus 2.24 reverse stir ng 0.52 0.02.88 0.11 6.66 0.994 0.52 type x 0.78 0.7 0.48 0.01 through 2.03 modular arithmetic 2.7 0 to 08 Don't yuam 0.9 free 9 no 0.785 sword to 2163 3 don't food dime to 0.6 we 3 2.7 food 1 2 by no su 3 non 99 p 0.47 solve equation 2 82 plus 0.063.24 plus 0.799.16 plus 0.6 up 2.303.5 -.492 0.492.96 or 1052 for 0.5.9128 cs duplicate string 0.57 and loss 0 then 05 1.33 to 13 2.22 for each 2.31 5.9 must 3 through 6 2.66 minus 0.76 my do 55 790.025.022.93 missing duplicate at 0.49 mana 0.040.71 mas 0.04849 plus 0.2731 mas 2.1.24 mas 0.35 at 6 and 0.02305 plus 0.01.72 0.30 odds first 0.55 plus 0.04 then 99 plus 0.05 Dix 3 not 1.344.49 2.81 1.67 0.3888 4 vine 4.45 to display 0.14 fu 7 1.7 binary addition 1.33 plus 0.051 35 plus 0.041 sp 36 plus 0.4469 2.94 2.9 buns 5.305 and 6 barrel waffle 1.4 binary multiplications 1.35 mas 0.06 1.37 sim.04 at 764 3 remains 2.76 2.06 1.37 1.34 no 45 x 4 1.95 compute score 0.95 minus 0.051 05 plus no 5 1.62 1.21 3.8 is 2.45 1.57 0.34 0.97 0.044 1 dunes 0.01 3.3 0 1.27 bucket sort 0.58 na 0.090 0.98 plus 0.08 60.7 2 5 through 2.24 1.34 0.76 0.70 5.64.54 plus 1.77 in the RNN experiment. The hyperparameters used include the learning rate, number of stack symbols, and random seeds, leading to 900 TPU units. An additional 300 TPU units were used for the phase transition experiment. For the CNN experiment, 800 TPU units were utilized. The scaling laws experiment employed 750 TPU units. The autoregressive experiments required 2,910 TPU units in total. The running times for each task and architecture are listed in Table A.2. Note that results were aggregated over hyperparameters, leading to higher standard deviation for transformers and tape RNN. The ND stack RNN has a slow training pace, being approximately 4 times slower than the classical stack RNN due to the computation of a large tensor GAIN representing transition weights. The memory space requirements for ND stack RNN can be intense. The tensor's size is proportional to L plus M3, where L and M are the input and output sequence lengths. The space needed is significant, making adjustments necessary to fit in memory. Additional experiments and main results are detailed in subsequent sections. Published as a conference paper at ICLR 2023, means and standard deviations computed over random seeds of the score, average test accuracy, see Section 4, for the results of the main experiment. The Th denotes permutation invariant tasks. The denotes counting tasks. The PIC denotes tasks that require a non-deterministic controller, and the TAS denotes tasks that require superlinear running time in terms of the input length. Level tasks, RNN stack, RNN tape, RNN transformer, LSTM, Riven pairs 100.0, 0.0, 100.0, 100.0, 67.7, 15.0. Modular arithmetic, simple. 100.0 plus 0.01 node point on 0.01 plus 0.23.1 was 0.81 was 0.0 parity check. 95.5 is 44.2. 100.0 0 1 by don't know is 0.5.4 plus 0.701 0.0. Cycle navigation 100.0 at 09 6.8.66 100.0 3.9 plus 10.5. Donomatis 10.8 DCF stack manipulation 54.5 1.1 93.8 50.16.9 was 22 then 65 1.11 was 8 1.7. Reverse string 60.4 minus 2.39 6.2 to minus 12.19.7 plus 15.6 set 1 plus 2.79 for 1.0 modular arithmetic 34.6 by 4.3 7.8 7.6 time plus 20 band civitate 8.2 4 3 1's 4.3 solve equation 31.3 8.4 6.1 to 7.3 7.7 12 plus 7 3 3.5 1.637.1's 14.0 CS duplicate string 50.21 plus 0.05 1.60 but 16.35 6.105 6.0.9 missing duplicate 51.7 was 0.253 on 6.6.1 to 23.3 8.1.5.6 odds first 50.4 tot 1.4.17 6.2 with 16.65 2.17 0 and 05 4.6 0.8 binary addition 49.5 ma 0.35 0.9 plus 0.974 3 plus 10.965 1.7 was 1 thrive 4.8 0.4 binary multiplication 49.6 miles 0.2 1.4 is 0.7 4.5 is 2 bears 3.6 with 2.9 plus 0.2 compute script 53.9 plus 6.13 by 6.20 pay points 1 by 4 5 time 7.0.2 bucket sorts 35 and 3.6 plus 6 16.3.6 slurf 10.8 5 and us 20 20.9 4 MISA 21.9 phase transition effect for the stack on reverse string DCF. For training ranges N10, the model fails to generalize to longer sequences as it memorizes the training distribution. The score in Fig is the accuracy shown in Fig averaged over sequence length's x-axis. That some models do not achieve a perfect accuracy within the training range U1N, such as in the Compute Score CS task. Phase transition under increasing training ranges. In this section, we investigate how much training data is needed to learn the data-generating grammars. For certain tasks and architectures, we observe a substantial phase transition of the test accuracy for different training ranges. For example, shows the generalization performance of stack RNNs on the reverse string DCF task for different training ranges. Clearly, the models fail to learn the data-generating algorithm when only exposed to sequences of length smaller than 10. We hypothesize that for small training ranges, the networks overfit to the training data, essentially learning a lookup table to recognize the small finite language. In contrast, larger training ranges encourage the networks to learn the data-generating algorithm that generalizes to sequences of unseen length. Published as a conference paper at ICLR 2023. Probability of stack action over sequence time step push pop no op 42024 PCA 1422 PCA2 PCA of the internal states even plus 0 even plus 1 odd plus 0 odd plus 1 A stack RNN on parity check R. Probability of stack action over sequence time step push pop no op 10 505 10 PCA 110 10 PCA 2 PCA of the internal states 01 EB stack RNN on reverse string DCF. Probability of stack action over sequence time step push pop no op 0 20 40 60 80 100 120 40 160 PCA 12 24 PCA 2 PCA of the internal states 0 1 2 3 4 EC stack RNN on bucket sort CS. Analysis of the stack RNN on the parity check R and reverse string DCF tasks. Left, the network does not use the stack on parity check and has the same state structure as a classical RNN. Right, the network uses the stack on reverse string, and the PCA of the states shows that they are clustered according to the last input token only. Analysis of state and memory dynamics. Stack RNN program analysis. Here we check that the stack RNN, which is our simplest memory-augmented network, performs as expected on some of our simple tasks. As mentioned in section 5.2, Fig B.2a, shows that on the parity check task, the network ignores the stack by only applying no op and pop actions, visualized on an unseen sequence of length 100. We recall that Fig 3a also showed that the PCA of the states is identical to the one of a simple RNN, as it only depends on the last result and the last input token. Moreover, Fig B2b demonstrates that on the reverse string task, the network always uses the push action until the first empty token is reached, whereupon it starts performing pop actions until the end, which exactly matches the algorithms we would expect a PDA to implement. Note that in this task, the number of empty tokens we append to the input sequence is equal to the length of the input sequence, and thus the total sequence is of length 200. Finally, Fig B.2c shows that the stack RNN can leverage its probabilistic actions to implement multiple counters and consequently solve counting tasks that are beyond deterministic context-free. Concretely, the stack RNN uses a mixture of push and no-op actions to simultaneously push incremented counters while keeping the previous counter values unchanged. Once the stack RNN has consumed the entire input sequence, it switches to a mixture of pop and no-op to decrement the counters for the different tokens. Interestingly, once the final token is reached, the stack RNN relies mostly on no-op actions, since it has learned that the remainder of the output string will contain the token of the highest value. Transformer program analysis. Setup. The transformer achieves a non-trivial generalization score 61.9% with baseline 20% on the cycle navigation R task, but it does not solve the task in terms of our definition of score 90%. Therefore, we analyze the network's internals, in particular the attention matrices, to understand which algorithm the network has learned and why it fails on very long sequences. We visualize the attention matrices in Fig B3. The color scale is dark blue for 0.0 and yellow for 0.5, not 1.0 to increase readability. Our transformer networks consist of 5 layers with 8 heads, and we show all of the attention matrices, i.e. 5 per 8, for a short input sequence of length 8. Note that the actual input to the network is of length 9 since we append an empty token to the input sequence from which we retrieve the output. Interpretation of the learned algorithm. On the first layer, the model uses only the last empty token and matches it with the tokens 0 and 2, clearly seen on matrices 1, 1, and 1, 2. Note that the task is to count the number of zeros, the number of 1s, and to do a subtraction modulo 5. This first layer is able to separate the different tokens. The output of the last token for each head is a weighted sum, softmax, of a single value, the token which is attended to, and the weights are all equal to a constant, which means the output of the last token is just the value of the token which is attended to. Then the other tokens have a constant weight over the whole sequence, which means that the output, published as a conference paper at ICLR 2023, the transformer attention mechanism computes a weighted sum of all tokens' values, with constant weights proportional to each token's frequency. This enables the network to calculate token occurrences individually in the linear layer for head integration. A scatter plot in Fig B.4 illustrates the network's activations after the first layer for sequences of length 20, supporting this concept. For long sequences, the constant weight scheme yields frequencies rather than true counts, scaled by 1 har n for sequence length n due to the softmax function. As a consequence, the network can generalize reasonably well to longer sequences, but not without limitations. Fig BB4 depicts the persistence of the structure for longer sequences with points converging, complicating class differentiation. Additionally, Fig B.5 displays the activation evolution in the final layer for increasingly longer sequences, showcasing the challenge in classifying due to the absence of clear clusters in the input activations. Bansal et al. 2022 demonstrated that fully convolutional networks exhibit strong performance on length generalization tasks, while Merrill 2019 proved the limitations of single-layer convolutional networks with max pool activation functions. To evaluate the length generalization capabilities, we examined a basic CNN architecture on our benchmark and visualized the maximum and average accuracies across test lengths in tables B.2 and B3. Despite using kernel sizes 3, 5, 7, 11, our CNN generally struggled with regular tasks, often achieving accuracy comparable to random guessing, aligning with Merrill's 2019 theoretical findings but conflicting with Bansal et al. 2022 results. Notably, Bansal et al. 2022 proposed a CNN architecture with an adaptable number of layers based on sequence length akin to adaptive computation time, Graves 2016, differing significantly from the classical CNN architecture under examination. Published as a conference paper at ICLR 2023, PCA1, PCA2 by number of PCA1, by number of PCA1, by number of PCA1, by output classes. Analysis of the transformer activations after the first layer on the cycle navigation task for an input sequence of length 8. We report only the first two principal components of sequences. We clearly see that the network learns to count the number of zeros, 1s, and 2s, and already separates the output classes very well after this first layer. PCA1, PCA2, length 20, PCA1 length 100, PCA1 length 200, PCA1 length 500. Analysis of the transformer activations after the last layer before the final linear logit layer on the cycle navigation task for an input sequence of length 8. We report only the first two principal components of sequences. We see that the activations form 5 clear clusters for short sequences, length 20, and slowly decay into the center, mixing the clusters together. Published as a conference paper at ICLR 2023. We evaluate the experiment suite from section 5.1 for the stack LSTMs and compare their performance with that of stack RNNs. We observe that stack LSTMs and stack RNNs perform roughly equally well when considering the score, maximum accuracy over the 10 initialization seeds, which is not surprising given that both networks are theoretically located on the same level of the Chomsky hierarchy. However, when considering the average, stack LSTMs perform worse. Our training protocol, gradient descent, is less stable for this architecture, confirming the results of prior work. We hypothesize that this is due to the fact that LSTMs are more powerful than RNNs, as they can implement K-counter machines, and thus do not always simulate a finite state automaton. This can be an advantage for more difficult tasks, e.g., counting tasks such as bucket sort, but also a disadvantage for simpler tasks that only need a finite state automaton controller to interact with the memory structure. We also compared the stack RNN and the stack LSTM to their non-deterministic counterpart, the ND stack RNN. We observed that this architecture performs well on regular tasks as the other memory-augmented RNNs. However, it fails on most tasks beyond regular, potentially due to its large action space, 24 actions, and the difficulty of training a tensor that tracks all possible stack values. Surprisingly, the architecture solves the missing duplicate task perfectly. In this paper, we chose to predict the output sequences from empty tokens, but we could also have chosen to predict the sequences autoregressively. Here, we conduct the same set of experiments, but in the autoregressive setting, to confirm that this aspect of our experimental setup does not impact the architecture's positions in the Chomsky hierarchy. For the memory-augmented RNNs, we replace the empty tokens with the true output sequence during training. However, to avoid predicting the input, we append an extra empty token between the input sequence and the true output sequence. We observe that these models trained with the autoregressive system perform very similarly to the ones trained with the empty token system. That is, this part of the training scheme does not affect the length generalization scores, and therefore does not change where the networks lie on the Chomsky hierarchy. Published as a conference paper at ICLR 2023. Score in percentage, i.e. accuracy averaged over all test lengths and maximized over 10 random seeds for the CNN, stack LSTM, and ND stack RNN. The results for the stack RNN are identical to Table 2. We consider a model to generalize successfully bold if its score is greater than or equal to 90%. The random accuracy is 50% except for cycle navigation, R, bucket sort, CS, and the two modular arithmetic tasks where it is 20%. We denote permutation invariant tasks with FOI, counting tasks with FOI, tasks requiring a non-deterministic controller with FOI, and tasks requiring superlinear running time with TEBs. Level tasks, CNN stack RNN, stack LSTM, ND stack RNN, Reven pairs, 50.100.0, 100.0, modular arithmetic, simple, 20.100.010.100, parity check, 50, 100, cycle navigation 20.110.100.100, DCF stack manipulation 52.4, 100.59.2, reverse through string 5.0, 100.106.2.4, modular arithmetic 31296.161.035.8, solve equation 20.156.2, 67.547.5, duplicate string 50.05285905192, missing duplicate 51.055.255.11, odds first 50.95.53.1, binary addition 49.827.60535, binary multiplication 49.952.753.3.9, compute sort 50.256.57650, bucket sort 29.178.199.2, 41.7 in section 5. We compared the transformer encoder to other sequence prediction models, as this allowed for a fair comparison. The original transformer architecture, consisting of a decoder, processes sequences autoregressively. Similar to memory-augmented RNNs, we observe that the autoregressive model performs roughly as well as the transformer encoder, but fails on the permutation invariant task bucket sort. The autoregressive model excels at solving the duplicate string perfectly. Suppose a neural architecture, e.g. a transformer, is limited to a particular algorithmic complexity class, level on the Chomsky hierarchy. In that case, no amount of scaling can overcome this limitation, putting a hard limit on what is possible via scaling. Specific neural architectures might be unable to implement certain classes of algorithms due to systematic limitations that are not overcome with more data or larger models, but can be overcome with architectural extensions, adding a stack or a tape to an RNN. Published as a conference paper at ICLR 2023, Table B3, means and standard deviations of the score for the results of Table B2. The results for the stack RNN are identical to Table B1 and are included only for easier comparison with the stack LSTM. The quote denotes permutation invariant tasks. The denotes counting tasks. The MOT denotes tasks that require a non-deterministic controller, and the KEX denotes tasks that require superlinear running time in terms of the input length. Level tasks CNN stack RNN stack LSTM endostack RNN riven pairs 50.1.100.0 98.5.7 modular arithmetic simple 20.0.11.010.0 0.0784 28.8 parity check 50.0 demo 0.10 Bratz 3.6 cycle navigation 20.0 and 196.86.7 7.7895 5.0 is 9.1 DCF stack manipulation 52.4 mala 0.09 3.8 is 15.6 6.1 70.4 for 5.1 mas is 2.5 reverse string 53.0 bow.19 sit 2 nas 12.194 no is 12.46 1.6 0.6 M earth 30.7 so at a 5.8 so 1.35 1.12 to 8.4 4.1 solve equation 19.9 knobs row 4 6.17.4 2.10 to 34.4 9.7 CSD duplicate string 50.05 1.6 by 6 0.6 6 point minus 1.3 fip 6 minus 0.2 missing duplicate 50.6 0.5 3.6 0.75 0.30.78 2.0 node 23.3 Odds first 50.0 0 5 1.5 11 5 4 4 and 0 and 7 2.8 binary addition 49.7 full 5.9 5 5 1 point binary multiplication 49.8 is 1 so 0.05 1.7 to throw 5 row 0.4 compute scored 51.3 of 6.1 0 3 of 7.254 0.3 per 0.4 bucket sort 28.4 and 0.65 6.6.16.28 1.7 19.92 Tabled score accuracy averaged over all test lengths and maximized over 10 random seeds for autoregressive setting. We only include the tasks with output length larger than 1 since the results are identical to those in table 2 otherwise. We consider a model to generalize successfully bold if its score 10-90%. The random accuracy is 50%, except for cycle navigation, bucket sort, and the 2 modular arithmetic tasks where it is 20%. We denote permutation invariant tasks with SLI, counting tasks with CLI, tasks requiring a non-deterministic controller with FO, and tasks requiring superlinear running time with TEX. Level tasks RN stack RNN transformer LSTM DCF stack manipulation 58.0 wonder 053.256.9 reverse string 63 at 100.53.5 CS duplicate string 50.35 through 70517 odds first 50.5 104 736 binary addition 41.723 binary multiplication 49.5 2.52253.3 compute squirt 54.1 57.852 458 not bucked sort 2952.84 and 492928 published as a conference paper at ICLR 2023 sequence length accuracy A even pairs 0.50 60 0.70.80 91.0 R. Sequence length accuracy. B. Modular arithmetic simple. 0.2 or 60 81 R. Sequence length accuracy. C. Parity check. 0.24.81.0 Sequence length accuracy. D. Cycle navigation. 0.50 60 is 70 80 910 Sequence length accuracy. E. Stack manipulate 0.50 60 70.80.91.0 DCF. Sequence length accuracy. F. Reverse string 0.20.40 60 81 0 Sequence length accuracy. G. Modular arithmetic 0.20 60 81 DCF. Sequence length accuracy. H. Solve equation 0.50.670.80.91.0 Sequence length accuracy. Transformer RNN, stack RNN, tape RNN, LSTMI. Duplicate string 0.5560.70.80.91.0 CS. Sequence length accuracy J. Missing duplicate 0.5060 70 80.91.s. Sequence length accuracy K odds. First 0.50 70.80.91.0. Sequence length accuracy L. Binary addition 0.5 Sequence length accuracy M. Binary multiplication 0.5 sig.80.91 CS. Sequence length accuracy N. Compute script 0.40 to 60.81.0 Sequence length accuracy O. Bucket sort. Published as a conference paper at ICLR 2023. Sequence length accuracy A. Even pairs 0.5 60 70.80 91 no. Sequence length accuracy B. Modular arithmetic simple 0.2 to 40 to 60 81 byte row. Sequence length accuracy C. C. Parity check 0.60 81 row. Sequence length accuracy D. Cycle navigation 0.50 60 80 91 byte row. Sequence length accuracy E. Stack manipulation 0.50 at 60.70.91 byte 0. Accuracy none. Original sin cos L transformer XL rope F. Reverse string 0.2 to 40 60.81.0. Sequence length accuracy G. Modular arithmetic DCF 0.40 byte 60 81.0. Sequence length accuracy H. Solve equation 0.50 60.78.91. Accuracy I. Duplicate string 0.567.91.0. Accuracy J. Missing duplicate 0.50 but 60.70.80.91.0. Accuracy K. Odds first 0.55 60 at 70 at 91.0. Accuracy binary addition 0.5 60 70 80 91.0. Accuracy M. Binary multiplication 0.5 60 80 91.0. Accuracy N. Compute sort 0.20 but 60 81.0. Accuracy O. Bucket sort, published as a conference paper at ICLR 2023. Means and standard deviations of the score for the results in the autoregressive setting. We only include tasks with output length larger than 1, since the results are identical to those in the table otherwise. Level tasks RNN stack RNN transformer LSTM CF stack manipulation 56.7 print 0.100.1 51 sef 1.3 55.8 dis 1. Reverse string 62.1 99 through 52.3 at 1b to 1.10. CS duplicate string 50.2 1.1 50.5 and 90.7 sevens 4 plus. Odds first 50 to 104 and through 1.02 52.3 is 1/4. 52.9 to 0.4 pen. Binary addition 49 4 pen to 2 penny. 50 to 5 pen and 5. 60 to 2 to 4 pen 2 and 50 to 1 pen 6. Binary multiplication 47 5 live 5. 55 plus 1.3, 58 to 5 plus 1 5. Compute scored for 5. Compute scored 50 at 7 to 7 1 5 3 for 4.58 5 5. Bucket sort. Total bucket sort 2028 plus 3.45 9.7 is 8.7 32.1 4 per 9.06. To provide a more detailed empirical result, we train the transformer encoder with relative positional encodings for increasing numbers of in-distribution data points, 100,000, 1,000,000, and 10,000,000 training steps, and increasing numbers of layers, 5, 10, 15, 20, 25. The score, i.e. the accuracy averaged over all test lengths, generally does not increase with more training data or more parameters. Thus, in this empirical setup, the Chomsky hierarchy implies a hard limit on scaling laws.